This short video will introduce you to the alcohol functional group. So to be an alcohol, what you need is this OH functional group, which we call a hydroxy group or hydroxyl group. Or you can call it the OH atoms. Okay, so as long as you look at your molecule, this short video will introduce you to the organic group known as the alcohols. What you'll notice about this organic group is when you look at the molecules, they'll have this OH group. We refer to that as the hydroxy functional group. Okay, so an alcohol will always have at least one of these. Now there are molecules where there are more than one. For example, where there are two, we refer to those as diols, but more on that in the next video. Okay, so one of the first things that we need to be able to do with alcohols is classify them. The process is like we did when we were looking at the haloalkanes. Focus in on the carbon that has got the functional group and then count the number of carbons adjacent to this carbon. So if you look at the 4 bonds, it is only bonded to one other carbon. So we would classify this as a primary alcohol. The carbon atom, which is bonded to the OH group, is bonded to one carbon atom. And a short way of representing primary alcohol is use a 1 with a degree symbol. Moving on to secondary. Again, focus in on the carbon with the OH group and count the number of carbons adjacent to that. Note the word adjacent means like neighbour. So it's got one carbon here on the right hand side, it's got a second carbon here on the left, but the other bond is to an H. And another point, carbons only ever have 4 bonds, never more, never less. So you've got 3 other bonds you need to look at. When 2 of them are to carbons, we would refer to this as secondary. The carbon atom, which is bonded to the OH group, is bonded to 2 other carbons. So it is a secondary alcohol, or the symbol 2 with that degree symbol. And finally, if your carbon, which is bonded to the OH group, has 3 adjacent carbons, which is the maximum that you would be able to have, given that the 4th bond will be to the OH group, we would refer to this as a tertiary alcohol. Again, the 3 with the degree symbol, representing those 3 carbons that are directly bonded to the carbon with the OH group. So there you go. Primary, where it's bonded to 1 carbon, secondary, where it's bonded to 2 carbons, and tertiary, when you've got the carbon with the OH group bonded to 3. Now I'll just quickly recap the haloalkanes and you'll see it's an identical system. The only difference is the carbon you're going to focus in on doesn't have an OH group, it's going to have a halogen atom. In these examples you've got the chlorine, which is a halogen atom. So here, 1 carbon attached, it's a primary haloalkane. When you've got 2 carbons adjacent, it is a secondary haloalkane. And finally, where you've got the situation of 3 of the adjacent atoms being carbons, that is tertiary. So once again, there's your short summary. So classifying whether it be alcohols or haloalkanes, very similar in that you just need to identify the functional group and then count the number of adjacent carbon atoms. Now, some very important terms that you must avoid using. Do not ever refer to the chlorine atom as being a molecule. So in this instance here, I don't have the chlorine, but you would not refer to that as an OH molecule or an O molecule. The whole entire chemical is the molecule. So when you're referring to parts of that, then we refer to them as atoms. Now the other term never to use in organic chemistry is the term ion. So you wouldn't refer to this as an OH ion, or in the haloalkane as a chloride ion or chlorine ion. Okay, so we don't use the term ion, they are atoms. Now it's absolutely fine, you can refer to it as the OH group, or you can refer to it as its name, which is the hydroxyl group. Writing the carbon bonded to the OH is sorry, I've stuffed this a little bit up. When you're writing, you can just say things like the carbon bonded to the OH is bonded to one other carbon. So you'll notice I haven't referred to that as a group, atom, ion, molecule. I've just referred to it as OH, and then I've just referred to it as carbon rather than carbon atom. And that is by far much more acceptable than using those wrong terms. I hope that hasn't confused you. Right, on to the trend in boiling points. So as an organic molecule gets larger, so too do the intermolecular forces between molecules. So what you'll see in this representation, although it's not alcohols I've got here, these are just alkanes, but if you've got a small organic molecule, there will just be a small intermolecular force. As the carbon chain gets increasing in length, the amount or the strength of the intermolecular forces also increases. Note that just because I've got here 5 lots of these red dashes which represent intermolecular bonds, it doesn't mean there's 4 bonds. It's just that is weak, that is stronger, and this is even stronger. Okay, so as the molecules get larger, and it doesn't matter if you're talking about alcohols or alkanes, it's the same idea, then you get these stronger intermolecular forces. And therefore, more heat energy is needed to break those stronger intermolecular bonds between those molecules. And so you'll have a higher temperature for their boiling point. Now, the trend for the melting point isn't quite the same, but it's a little bit beyond level 2. It's got a reference to this small polar OH group, but we won't need to know that for our level 2 course. The other thing I wanted to point out is the terminology. Whether we're referring to them as intermolecular forces or intermolecular bonds, they're the same thing. Okay, so the trend for alcohols is the same as what we learned for alkanes, and it's due to the same idea, the intermolecular forces getting stronger. Okay, the next thing that you're going to need to know about is solubility. Now, this is the opposite in terms of trend. As the molecules get larger, they become less soluble. Their solubility decreases. And the reason for that is as the carbon chain, which is often referred to as the alkyl portion, note that alkyl is like alkane, alkene, like it's the carbon-hydrogen section. As that gets longer, the alcohols are unable to form intermolecular bonds with the water. Okay, so small alcohols are soluble due to having this OH group, and that is because the small alcohols are polar and they can form intermolecular bonds with the water, so that makes them soluble. Another word we use for soluble is miscible. Now, as the larger alcohols cannot form these intermolecular bonds with water, they are immiscible. I need to explain this a little bit further, so follow through. So this is what we would refer to as a small alcohol, okay? And this section here in red, which is the hydroxyl group or OH group, it is polar and it is able to form intermolecular bonds with water, which is also polar. And you'll see it can form another intermolecular bond here. So because they can form these weak attractions, these are soluble. the water and the ethanol are able to mix. Okay, they are miscible or soluble. Now, the problem that happens is while the OH group is polar and can mix with water, the carbon-hydrogen groups or atoms here, which I've referred to in a previous slide as the alkyl group, this is non-polar, and non-polar cannot mix with water, which is polar. Now, one way to remember this, but don't quote it in an exam, is like dissolves like. So polar can dissolve in polar. Water is polar, you see. So the problem is that when you've got this large portion that's non-polar, then it stops being soluble. So as long as you're a small alcohol, then your polar OH group will mix with the water, and that's fine. So this is water and ethanol, and you'll see it's all single solution because it's mixed or miscible. And this one here, you'll see again 3 carbons, it's able to mix. So these are small alcohols. Now when you get to 4 carbons, you'll get the 2 layers forming, and that is because butanol has got the 4 carbons in the long chain, and that's non-polar, and that starts then to decrease the solubility. So small alcohols are able to mix with water, so soluble or miscible. They become less soluble when they have these 4 carbons in length, but when you get more than 4, then they really don't mix whatsoever. Okay, they do not mix, so immiscible. Right, so that's where I'm going to stop here today. There's one last final point that I'll point out for extras for experts, and that is you'll notice sometimes people use hydroxy and sometimes they'll refer to it as hydroxyl. It doesn't matter for level 2. You will not get marked down for using hydroxyl instead of hydroxy. But if you want the technical right answer, whenever you're referencing the functional group, then we do write it hydroxy, and you'll notice we've omitted the L, okay? But when you're referring to it as a hydroxyl like radical, that's when you are to put the L in, okay? So it's fine to refer to it as the hydroxyl group. But as I say, not important, and it's only a little extra if you were wondering why sometimes there's a hydroxy and sometimes there's a hydroxyl. Okay, thanks for listening.